Hari Om. In the fifth module of microprocessor course, we are currently discussing the three different data transfer schemes. We have seen data transfer takes place between CPU and memory, CPU and input-output devices, memory and input-output devices. We have seen what are the major differences between these devices during the data transfer. To solve the problem of speed mismatch, different data transfer schemes have been developed. And the three important data transfer schemes are programmed input-output, interrupt-initiated input-output, direct memory access. In our previous video, we have discussed what is programmed input-output. And we have seen in the programmed input-output, the CPU has to stay in a program loop until the input-output unit indicates that it is ready for data transfer. So the CPU will be wasting lots of CPU cycles because it has to check the status of the device before the data transfer. It has to continuously check whether the device is ready for data transfer. So by the time the CPU cannot engage in any other program execution. So to overcome this difficulty, we have interrupt-driven input-output. This is an alternative scheme dealing with input-output. Now here in the interrupt input-output, we are going to see how the problem of programmed input-output is overcome. So when you take the interrupt initiated input-output or interrupt driven input-output, this technique is used to overcome the limitation of programmed input-output, because in the programmed input-output, the processor has to verify the status of the input-output module. Whereas in the interrupt-driven input-output, what we are going to do, instead of making the processor to verify the status of the input-output module, it becomes the responsibility of the input-output interface, or you call it as input-output module, to intimate the processor by an interrupt signal. So what happens now? The CPU can do some other execution if the input-output device is ready for data transfer. It will interrupt the CPU saying that I am ready for data transfer. Whether it is input or output, the device will inform the processor saying that I am ready for the data transfer. And the CPU will respond to interrupt signal and branches its execution to service the interrupt using the interrupt service routine. ISR is nothing but interrupt service routine. So this is how it happens. The CPU will be having the input-output system connected, and the interrupt request will be given, and the interrupt acknowledgement will be given by the CPU. The input-output system will be giving the interrupt request, and the CPU will be giving the interrupt acknowledgement. So now what happens? You can observe this diagram. Here the main program, the CPU will be executing this program. Imagine the CPU is now executing the program. Here at this particular point, the interrupt occurs. Now when I say interrupt occurs, the CPU is to transfer a data to the input-output device. By the time the interrupt signal will be generated by the input-output device, and it will interrupt the execution of a program. So when an interrupt occurs, the system, or let me put it this way, the processor branches its execution from this program to an interrupt service routine. So this interrupt service routine is nothing but the handler for input output operation. So all these statements will be executed. Then it will come back and execute the next instruction of the main program. The next instruction where it gets interrupted. So this is what happens when the main program execution is interrupted. It will request the device to get ready, and it will check the next instruction and execute the data, and it will check for the interrupt. If there is an interrupt, the interrupt service routine will be executed. This is the interrupt service routine. If there is no interrupt, it will continue with the execution of the next instruction. So the execution of next instruction will happen here. If there is an interrupt, the interrupt service routine will be executed. So when I say interrupt service routine, it will have set of statements like this. So it will start the interrupt service routine and it will save the CPU status. Why it needs to save the CPU status? Because the main program will be having a different status, whereas interrupt service routine will have a different status. And not only that, all the registers and flags that are used by the main program will also be used by the interrupt handler. So what the CPU will do, before branching to interrupt service routine, the current status of the main program will be saved, then it will branch. So that is what happens here. The CPU status will be saved, then it will be executing the data transfer. Where do you have these instructions for data transfer? It will be available in the interrupt handler. Then once the data transfer instruction is executed, it will restore the processor status. So whatever status is saved here, that will be restored. Then it will be enabling the interrupt. Then it will go back to the main program. So this is what happens when an interrupt occurs. So the CPU will be responding to the interrupt signal and it will branch the execution to service the interrupt. How? By using the interrupt service routine. Now, whenever the CPU is responding to interrupt signals, and it will be storing the return address from the program counter. Why? Because it has to return back to the execution of the main program. So it will save the return address from the program counter into the memory stack and then control the branches, and then the control branches to the interrupt service routine. Now the interrupt service routine processes the required input-output data transfer. After completion of executing interrupt routine, CPU returns to the previous program, the main program, and continue what it was doing before. So this is what happens in the case of interrupt driven input-output. So the main program, the next instruction will be fetched in the sequence and the instruction will be executed. And by the time after executing one instruction, the CPU checks whether any interrupt is activated. If so, it will execute the interrupt service routine. Otherwise, it will go back and fetch the next instruction for execution. So in the interrupt service routine, the interrupt driven input output is the alternative scheme or the second mode of data transfer, which is dealing with input output. And the interrupt input output is a way of controlling input output activity whereby a peripheral or terminal that needs to make or receive data transfer sends a signal. So what happens now? CPU is not going to check for the status. The device will be sending a signal to say that I am ready for the data transfer. So this will cause a program interrupt to be set. Okay, and not only that, at a time appropriate to the priority level of the input output interrupt. When I say priority level, we will have more than one peripheral devices. So depending upon the depending upon the device priority, the interrupt will be accepted by the CPU or acknowledged by the CPU. Suppose if there are more than 3 peripheral devices and all the 3 peripheral devices are simultaneously sending the interrupt signal, by the time based on the priority of the input output device, the input output interrupt will be handled. So in the interrupt driven input output relative to total interrupt system, the processor enter into the interrupt service routine. So when you have 3 different peripheral devices, 3 different interrupt service routine will be available. The corresponding routine will be executed. The function of the routine will depend upon the system of interrupt levels and priorities that is implemented in the processor, which we have already seen. Now the interrupt technique requires more complex hardware and software, but makes it more efficient use of the computer's time and capacity. That is the advantage. Though the interrupt technique is complex in the case of hardware and software, but it gives efficient usage. So imagine if the user is not pressing the keyboard for the input operation, if the user is not pressing the keyboard for 3 seconds or 4 seconds, or for all the 4 seconds, the CPU cycles will be wasted. So that is one of the disadvantage of programmed input output. Now what happens? If the user is not pressing the keyboard, by the time the CPU can execute some other instructions, some other program, if it is a multiprocessor or multitasking environment, some other programs can be executed. At the same time, it will be waiting for the input output device to send the signal. So during the execution of another program, the CPU will wait for the interrupt. If there is an interrupt coming from the input output device, it suspends its execution and it will branch to the interrupt service routine. In the interrupted input output, it issues an interrupt request signal when the data are available from the device. So when the data is transferred, we have seen here the data will be received in a data register. So when the user presses the key, the data will reach to the data register. So when the data is coming to the data register, by the time the CPU will get a interrupt. Right? So until it gets a data in the data register in the input output interface, the CPU can proceed to execute another program. And the interface will keep monitoring the device. When the interface determines the device is ready for data transfer, it generates an interrupt request to the computer. Now, upon detecting the external interrupt signal, the CPU will momentarily stops the task it is processing and it branches to the interrupt service routine. So, this is what happens, and it says you require more complex hardware and software. So this is what we require in the software and in the hardware for processing the input output. Now in the case of hardware, you need some interrupt controller to generate the interrupt signal. In the same way, to acknowledge the interrupt from the CPU also you need the hardware. Whereas to process the input output instructions, you need a interrupt service routine, which will be the software. So in the hardware, what are the things you require? A device controller or some other system hardware issues an interrupt. So generally it will be the input output device controller. and then the processor finishes the execution of current instruction. This is very important. Even though the interrupt happens in between the execution of an instruction, the instruction will be completed or finished by the CPU. Only then the processor signals the acknowledgement of the interrupt. In between the program, the interrupt can be acknowledged, not in between the execution of an instruction. Then the processor will be pushing the program status word. PSW is what you call as program status word, which is nothing but the status of the current program, execution status of the current program. That is what you call as program status word, and the program counter. Why? The program counter is the one that stores the address of the next instruction. So when it is executing instruction 1, the address of instruction 2 will be stored in the program counter, right? So during the execution of instruction 1, if there is an interrupt coming in, the address of instruction 2 must be stored somewhere. Where will you have an address of instruction 2? That will be available in the program counter. So both the program counter and the program status word, or sometimes it is also called as process status word, that will be saved somewhere into the control stack or in the memory stack. Then the processor will load a new PC value. What do you mean by new PC value? Address of the interrupt service routine, because it has to branch to the interrupt service routine and all the instructions of interrupt service routine must be executed, right? So what it has to do? The processor will be loading the new program counter, value based on the interrupt. Now what happens in the case of software? In the software, the remainder of process status information, everything will be saved somewhere, and the processor will be executing the interrupt. Once the interrupt service routine is executed, it will restore the process state information or program status word, and it will also restore the return address from the memory stack. Where will you have the return address? So whatever return address we had in the program counter here, so that is saved in the memory stack. So that will be restored from the memory stack. What are the things that will be restored? Both program status word and the program counter value. So both will be restored and that will be executed. Now if it is going to be the interrupt from the input, the device interrupts the CPU when new data has arrived and it is ready to be retrieved by the system processor. So that means inside the data register, the key press value has been received. So the input device interrupts the CPU when new data has arrived and it is ready to be retrieved by the system processor. Whereas if it is output device, the output device delivers an interrupt either when it is ready to accept a new data or to acknowledge a successful data transfer. So that means a data is already put in the data register which has to be taken by the output device. So when the output device is ready for accepting the data or it is successfully transferred the data to the output device, in both cases it will be interrupting the CPU. So here in the interrupt driven input output, CPU works on its given task continuously. When an input is available, the CPU is interrupted from its work to take care of the input data. The CPU can work continuously on a task without checking the input device. and here it allows the device themselves to interrupt it as and when necessary. So these are the basic operations of the interrupt. The CPU issues a read command. The input-output module gets the data from the peripheral while the CPU will be doing some other work. And the input-output module interrupts the CPU when the data is ready, and the CPU requests the data now, and the input-output module will transfer the data. So this is what happens in the case of interrupt-driven input-output. So if it is a read command, the input-output module get the data from the peripheral by the time the CPU will do some other task. So when the input-output module gets the data from the peripheral, it will interrupt the CPU. Then what the CPU will do? The CPU will request the data from the interface unit, and the interface unit will transfer the data. So this is what happens in the case of interrupt driven input output. So the point that you have to remember here is the CPU cycles need not be wasted in checking the status of the peripheral device. Instead, when the peripheral device is ready for data transfer, it sends a signal which you call as interrupt signal. So when there is an interrupt signal coming in, the processor will branch from the main program and it enters into interrupt service routine. So if I want to have this setup, the interrupt technique requires more complex hardware and software. So it requires a controller which generates the interrupts. The same way, it needs to get acknowledged by the CPU. By the time the process status word and the program counter content must also be saved somewhere. So these kind of hardware setup is required, and in the software, the program status word and the program counter will be copied from the registers to the memory stack, and the interrupt will be processed. Once the interrupt is processed, what kind of interrupt instructions we will have for the input operation as well as for the output operation. So this instruction will be executed. Then it will go for restoring the process status word and program counter content from the memory stack so that it resumes the execution of the program. So this is what happens in the case of interrupt driven input output. Let us discuss the direct memory access in the next video. Thank you.